All right, let's talk about probability. It's one of those things where our gut feelings can lead us completely astray. Today, we're going to dive into some classic puzzles that seem, well, kind of impossible at first glance. But you'll see that with the right tools, they're not so scary after all. Let's jump in.
So, let me hit you with a question right off the bat. Imagine a super accurate medical test for a rare disease. You take the test and it comes back positive. Now what's your immediate reaction? Probably panic, right? You probably think, well, that's it, I have it. But what if I told you the actual chance you have the disease is shockingly low? We're going to come back to this and solve it, and I promise you the answer will surprise you.
Okay, first up, we're going to learn a fantastic little trick. It's for solving a problem that sounds complicated, figuring out the odds of something happening at least once. Instead of doing a ton of messy math, we're just going to flip the whole problem on its head.
So here's the key idea. The phrase, at least one, is the literal exact opposite of none. They're two sides of the same coin. In the world of probability, we call this the complement. And it means that if you want to find the probability of getting at least one, it is so much easier to first figure out the probability of getting 0 and then just subtract that from 100%. It breaks down into a really simple 4-step method. First, you just define what you're looking for. Event A is getting at least one of something. Step 2, you figure out its opposite, which we'll call not A. That means 0 of that thing. Step 3 is the only real calculation. Find the probability of getting 0. And finally, you just do 1 minus that number. It's a really slick and powerful shortcut.
Let's make this concrete. Imagine there's a factory, and it's known that 15% of its products have a defect. You go and buy a dozen of them. So what are the odds that at least one of those 12 items is going to be faulty? Now, you could try to calculate the odds of getting 1, plus the odds of getting 2, plus the odds of getting 3, or we can use our new trick.
Get this, the answer is a massive 85.8%. That's probably higher than you guessed, right? So how do we get there so fast? Well, instead of dealing with all those possibilities, we just asked, what's the probability that none of them are defective? The chance of one item being good is 85%, or 0.85. So the chance of all 12 being good is just 0.85 to the power of 12. You subtract that tiny number from 1, and bam, 85.8%. For a company, a number like that is a huge red flag for their quality control.
All right, with that tool in our back pocket, let's move on to the next big idea, conditional probability. This is all about how probabilities are not static. They change when we get new information. The magic words you're listening for here are given that. So what is it formally? It's the probability of some event B happening on the condition that we already know for a fact that event A has happened. We write it like this: P, then a B, a vertical line, then an A. You can just read that out loud as the probability of B given A. It's all about shrinking the world of possibilities based on what we already know. Now, you could solve these with a fancy formula, you can see it right there, but honestly, there's a much more intuitive way to do it that's way easier and less likely to trip you up. You just assume the given thing has already happened. That shrinks your universe down. Then, you just calculate the probability within that new, smaller world. Let's see how that works.
We're going to use this table from a study about drug screening. It breaks down the results for 555 people. You can see who uses drugs and who doesn't, and what their test results were. We've got our true positives, false negatives, false positives, the whole shebang.
Okay, first question. What's the probability that someone gets a positive test result, given that we know they use drugs? Using that intuitive approach, we can just completely ignore the bottom row. Our entire world is now just those 50 people in the top row. So looking only at that top row, we see there are 50 drug users in total, and 45 of them got a positive test. So it's just 45 divided by 50. That's 0.9, or a 90% probability. Pretty straightforward, right? But now, let's flip the question. And this is where it gets really, really interesting. This time, what's the probability that someone actually uses drugs, given that they got a positive test result? It sounds almost the same, but it's a totally different question. This time, our universe shrinks to just that first column, everyone who tested positive. If you look at that first column, a total of 70 people tested positive. But, and this is the important part, of those 70 people, only 45 are actually drug users. The other 25 were false positives. So 45 divided by 70 gives us about 64.3%. See how different that is from 90%? That's a huge gap.
This brings us to a really critical mistake in thinking that people make all the time. It's sometimes called the inverse fallacy. And what we just proved is that the probability of A given B is almost never, ever the same as the probability of B given A. You can't just flip them.
To make this crystal clear, think about this. What's the probability that it's dark outside given that it's exactly midnight? Well, that's 100%, right? Of course it is. But now flip it. What's the probability that it's exactly midnight given that it's dark outside? Well, it could be 9 p.m., it could be 4 in the morning. The chance that it's exactly 12 o'clock 000 is practically zero. Confusing those two is a massive trap.
So now we can finally put all these pieces together with one of the most important ideas in all of statistics, Bayes' theorem. You can think of this as the formal engine we use to update our beliefs, to change our minds when we get new evidence. This is exactly what we need to solve that medical test puzzle from the beginning.
Okay, so here's our scenario again. There's a cancer that affects 1% of people. We have a test for it. If you have cancer, the test catches it 80% of the time. That's our true positive rate. But if you don't have cancer, the test still messes up and says you do 10% of the time. That's our false positive rate.
The easiest way to solve this, trust me, is to just invent a population. Let's imagine 1,000 people. Since the cancer rate is 1%, we'd expect 10 of those people to have cancer and the other 990 to be perfectly healthy. That gives us our totals for the rows.
Now we just fill in the boxes. Of the 10 people who actually have cancer, the test is 80% accurate. So 8 of them will get a positive result and 2 will get a false negative. Now for the 990 healthy people, the test has a 10% false positive rate. That means 99 of them, almost 100 people, will get a scary but incorrect positive result. The other 891 will correctly test negative. And just like that, our table's full.
And now we can finally answer the question. What's the probability someone has cancer given that they got a positive test? We just zoom in on that first column, the positive test results. In total, we have 107 people in that column. That's 8 plus 99. And of those 107 people, only 8 of them actually have cancer.
So we just do the math. 8 divided by 107, that comes out to about 0.075, or just 7.5%. Let that sink in for a moment. You get a positive result from a test that seems pretty good, and yet there's only a 7.5% chance you're actually sick. Why? Because the huge number of healthy people creates a much larger number of false positives than the small number of sick people creates true positives. It's totally counterintuitive, but the math is clear.
What we just did here is the heart of Bayesian thinking. We started with what's called a prior probability, our initial belief, before we knew anything else. In this case, that was the 1% chance anyone has cancer. Then we got new evidence, the positive test, and we used it to calculate a posterior probability. Our belief was updated, revised from 1% all the way up to 7.5%.
And this way of thinking, of systematically updating our beliefs as new information comes in, it's just an incredibly powerful idea. It goes way beyond medicine. It's used in science, in court cases, in artificial intelligence, and we can use it in our own lives. It's a way to be less wrong over time. It makes you ask not just, what do I think is true, but also, what evidence would it take to actually change my mind?